Good afternoon. My name is Neil Agarwal, and I'm excited to share with you today our work on building general-purpose accelerators for retrospective video analytics platforms. This work was done in collaboration with my advisor, Ravi Netravali. Increasing camera deployments have led to an unprecedented amount of video footage being continually captured. And while this is often processed in real time, it's also stored for after-the-fact querying and analysis. Such retrospective queries fuel a wide range of applications, from retail and business analytics to city planning to sports analysis. At the heart of executing these queries is running a machine learning pipeline. Given a video dataset to analyze, an ML model runs in every video frame, locating and characterizing objects with high accuracy. The challenge with these pipelines for retrospective querying is the sheer amount of computation involved necessary to run these machine learning models on these massive video data sets, which ultimately has implications on resource costs and query response times. To deal with these challenges, a variety of systems have been developed. The predominant approach is to pre-process the video by identifying similar groups of content throughout the video in order to reduce the number of frames on which you have to run the query model on at runtime. For example, some systems run a compressed model on the entire video to extract objects. Then, visually similar objects are clustered so that the full model only needs to be run once per cluster. And while this approach of baking in a specific model into pre-processing was promising for the earlier days of video analytics platforms, where the platforms themselves picked the models that the analysts could query with and decided what pre-processing to perform, today that's rarely the case. Today, datasets are queried with diverse models. For the same dataset, different analysts will use custom models that are tailored to their specific application needs. Or a single analyst will use different models over time as their models improve or their needs change. And as a result, the query model is often different from the pre-processing model. And this becomes a significant issue because these models tend to behave very differently on the same image data, even when trained for the same task. Different models, when applied to the same set of frames, can differ in what objects they find, what labels they assign to them, and how they localize them. Fundamentally, the way a model perceives and characterizes a given frame is a function of how and on what it was trained. The implication of this is, in our toy example, if you were to pre-process with model 2, but query with model 1 for the number of cars, you would get an accuracy of 66%, which is far below what applications need from analytics today. To understand how this arises in the context of real images and models, we performed a study. We collected a number of different machine learning models that varied on their training dataset, their model architecture, or both. And we find that even from a subset of our results, a mismatch of the model used for pre-processing and the query model can result in accuracies as low as 16%. This happens when you vary just the dataset or just the architecture as well. And we find this to be true across our entire dataset for different objects of interest and types of queries. Therefore, our work, Boggart, asked the following question: how do you pre-process video data to accelerate retrospective querying with diverse user-provided models? To answer this question, we can begin by enumerating the requirements of pre-processing. First, it has to be relatively cheap, since queries may never come in, and you want to avoid the potential for wasted work. Second, it has to be general purpose and comprehensive. We want to be able to accelerate diverse user-provided models. And third, the output should provide acceleration opportunities. In other words, a way to link information across frames in order to perform less inference at query time. To achieve these goals, we observe that aside from using deep neural networks and machine learning models to analyze video data, there's a rich body of classical computer vision techniques that already exist. And unlike ML algorithms that bake in a specific characterization of the video data, these CV algorithms can comprehensively and generically extract information from video. Therefore, Boggart's approach is during pre-processing use these traditional computer vision techniques to extract trajectories of potential objects based on motion patterns. This provides a way to extract important information about the video and then link it across frames. It's also much cheaper than using ML models or even compressed ML models. However, these computer vision algorithms tend to be less accurate and precise than machine learning models. So during query time, we judiciously run the query model to label the trajectories and correct these imprecisions in the pre-processing results. So now I'll describe each of these phases in more detail, and we'll begin with pre-processing. The output of Boggart's pre-processing on a video is a set of potential objects, denoted by a pair of coordinates, each labeled with a trajectory ID. In this visualization, a different ID corresponds to a different color. Now, in order to extract this information, Boggart leverages a sequence of various computer vision techniques, and let's briefly walk through them. First, Boggart builds an estimate of the background scene. Then, it subtracts the background from each frame to generate a foreground. Pixels in the foreground correspond to areas of motion. We then apply a series of morphological operations and connected component analysis to extract bounding boxes from the foreground. We call these potential objects blobs. Then for each blob, we extract key points, which are essentially unique pixels of interest, say on the edge of a windshield or on the tires of a car. And each of these key points come with descriptors that describe the content around each of the pixels. And so what's neat about these key points and their descriptors is that they can be matched across frames. So the idea is if there's enough key point matches across two blobs on consecutive frames, we can link these blobs and say that they are now a match. We can apply this matching technique across frames and transitively link their output in order to build long-running trajectories of blobs across frames. Now, while none of these CV techniques are new, what's important and different is how we use them in Boggart. In contrast to their intended use cases, we had to carefully tune them to be conservative, right? The priority of pre-processing is to comprehensively extract information. We can always filter out irrelevant objects or trajectories at query time, but if an object is missed at pre-processing, we have really no way to recover it later on. So now that we've extracted these trajectories, let's discuss what happens at query execution. Here, the idea is to run the model on as few frames as possible and use the trajectories to propagate model results to the remaining frames. The challenge with this, though, stems from Boggart's decision to use these coarse-grained CV techniques at pre-processing. We find that Boggart's pre-processing outputs often do not exactly match up or align with the outputs of these machine learning models. For example, the coordinates of the blob bounding boxes are imprecise relative to what the model would output, or the ML models can be inconsistent in the way they locate and characterize objects. Here, the model misses the car on the middle frame, but finds it on the first and the third. What this means is we need a new set of techniques to first identify the smallest set of frames on which we need to run the model, and correct imprecisions during model result propagation across the remaining frames. In the interest of time, I'll describe the high-level approach of our solutions. First, we observe that the number of frames on which you need to run the model depends on the level of dynamism and activity present in the video and its interaction with the query model. Correspondingly, we cluster different segments of the video based on video-specific properties that characterize the level of dynamism, and we profile small portions of each cluster to identify the necessary amount of model inference. To correct imprecisions in the pre-processing outputs, we leverage an observation about the relative position between an object's key points and the model's bounding boxes to dynamically correct the coordinates of blob bounding boxes found at pre-processing. So we evaluated Boggart on 96 hours of publicly available camera footage. Due to limited time today, I will focus on the first two axes of Boggart's evaluation results. First, we evaluate Boggart's query response times relative to a naive baseline that runs the model on all frames. For example, consider the following query: a model that's YOLO v3 trained on the COCO dataset, an accuracy target of 90%, and a binary classification query. For this query, the output of Boggart achieves an accuracy of 93%, thereby meeting the target. And Boggart does this while only having to run the full query model on only 5% of the total number of frames in the video. We perform this for additional query types, such as counting, where you count the number of objects in the frame, and bounding box detection queries, where you try to get the actual bounding box coordinates of each of those objects. We do this for additional query models, 3 different popular architectures trained on 2 different data sets to get 6 different models. And we did this on different accuracy targets. Across these queries, we find that Boggart consistently meets the specified accuracy target while running the model on only a fraction of the total frames. And all of these results leverage the same set of pre-processing results that were computed once per video, not once per model. And you'll notice that as the queries become more challenging, whether it's a more complex query type like finding the bounding boxes or a higher accuracy target, Boggart automatically adapts by running the query model on more frames to meet the required accuracy. And the reason is that such queries require higher levels of precision, therefore shorter propagation distances and more corrections to be made during query execution. Also kind of interesting is that querying for different objects requires varying amounts of model inference. For example, when Boggart is queried for people, it runs the query model on more frames than for cars. And the reason is intuitive. People are smaller and feature more model inconsistencies. Cars are more rigid and provide more stability during result propagation. We also compared Boggart to model-specific pre-processing approaches. For example, Focus trains a compressed model to approximate the full query model and uses that to extract and cluster objects during pre-processing. Boggart enables speedups that match or exceed those of Focus across different query types, despite Focus having complete knowledge of the query model during its pre-processing. This highlights Boggart's trajectories as a suitable model-agnostic alternative for result propagation across frames. Further, Boggart is able to outperform Focus on more complex queries, such as counting and bounding box detections, because Boggart can rely on these cheaper model-agnostic techniques to correct the imprecisions in the pre-processing output, where Focus can only correct these imprecisions by running the model on more frames during query execution. I also want to mention that Boggart's pre-processing is faster and doesn't require GPUs, unlike Focus. Further, Boggart's pre-processing runs once per video to support all future models. But to avoid accuracy drops, Focus would have to run pre-processing for every model it wishes to support, leading to higher costs and potential for wasted work. I would ask you to see the rest of the paper for the rest of our evaluation. In conclusion, Boggart is a general-purpose accelerator for retrospective querying with diverse user-provided models. It leverages lightweight, model-agnostic computer vision techniques to generate trajectories of areas of motion. We find that despite its generality, Boggart speedups match and most often exceed existing approaches. We have released our source code at the following link. And with that, thank you very much, and I'm happy to take any questions.